So, quick review. We said we can't use mgh for gravitational potential energy. We have to use this much more cumbersome negative big G, big M, little m over R when we go cosmic. Why negative? Where did we define zero potential energy? Out at infinity, we said that's when you wouldn't fall because you had no gravitational potential energy. And so how much energy must you have if you won't fall? Zero. But that meant because you were doing work to get to zero, you were starting out with less energy and increasing your energy to get to zero, you had to be starting with negative. Because we defined zero out at infinity. We could have defined it somewhere else, but it made more sense to define it there. We said this was about the most intense calculating that you're going to do. In fact, I introduced to you the notion of ditto marks and backspacing and editing rather than trying to type this all in. In fact, Hannah, this is where my love of let's get the thing by itself died an ugly death. I said, no, I'm going to turn it into one number first, then I'll get the thing on the other side by itself. We did a question that involved conservation of energy. G. We did a question involving work. We did a second question involving work. Example 3, a missile is launched from the surface of the Earth, but let's decide as a thought experiment, we're going to ignore air resistance. We're going to fire all of its fuel instantly in an initial burst. So on the launch pad, it leaps to full speed instantly and then coasts the rest of the way. As it rises, what happens to its kinetic energy and its orbital potential energy? So if we fire a rocket, if we burn all of the rocket fuel instantly and then let it coast, what will happen to its kinetic energy as it leaves the Earth? It's going to slow down because gravity's constantly tugging at it. So no, no, yes, yes. In fact, I would cross out A and B because I know they're wrong. What happens to its orbital potential energy? Why? Where does that kinetic energy go? It's got to go somewhere. So it's going to increase, not decrease, increase, not decrease. What's the correct answer here? Got to be C. Got to be C. And that's really all rocket fuel does. It exchanges kinetic energy to increase your potential energy. Can we ever get your potential energy to zero? Yes, we call that escape velocity. We'll look at that in the next lesson. Example 4. I like example 4. I like example 4. Example 4 is a nice question. A satellite is placed in a stable orbit. Did I say orbit? I can definitely say, if necessary, gravity is what's pulling me in a circle. With a speed of 4,200 meters per second. A says find the orbital radius. B says find how much work required to put it into orbit. Okay. A. Hannah, what's A want me to find? Did you say orbit? I think my first thought is going to be gravity is what's pulling me in a circle. I might try doing this. Fg equals Fc. Big G, big M, little m over R squared. Can you see, by the way, it's really easy to confuse this with potential energy and leave off the R. So be just really careful. This is why I've continued to say it all. If you get your formula sheet out, get in the habit of looking at your formula sheet, double check, triple check. Make sure you're using the force equation when we're talking about force. Make sure you're using energy when we're talking about energy. And that's going to equal M. Which AC am I going to use? How do you know? Okay. One of the R's is going to cancel because they're on the bottom. The little m cancels. That's good. Oh, although they gave me the mass of this. I was going to say they didn't give me the mass. They did, but don't need it. Hannah, what did you say they're trying to ask me to find? Where's the R right now? Ugh. I'm going to multiply it there and divide by v squared. I think we'll get this. orbital radius is what? Big G, big M over V squared. Is that correct, folks? Do I need to square root? No square root this time. Okay. So our orb is going to be 6.67 times 10 to the negative 11. Are we around the Earth? Doesn't say, so we assume Earth. 5.98 times 10 to the 24th divided by 4,200. Don't forget the squared. What do you get, folks? This is worth practicing typing in, because these are some pretty complicated calculations we are doing. And I did show you how to build the Death Star last week, right? Okay. Someone's going to put their phone on vibrate because, you know, they're not that important. Do you get 2261145.1.25? Okay. I'm going to store this on my calculator because I am going to want to use this. But for now, as an answer, I'll go 2.26 times 10 to the 1, 2, 3, 4, 5, 6, 7. Units, Hannah, it's a radius, so... Yep. Good. Okay. Hoi. By the way, I should just make sure none of you have forgotten about your French exam that you're writing. You all remembered? Okay. Nusaiba, what does B want me to find? Keep reading. Required to in orbit. Here's what that means. First of all, can I just go, don't write this down. Why can't I go force times distance? Gravity is changing. So we have to use the work energy theorem. Change in potential plus change in kinetic. Are we in orbit? Are we in orbit? Are we in orbit? Yes. Yes. So here's what that means. This is not going to cancel. If it was just lifting it up and dropping it back down, the change in kinetic would be 0. We're going to have to find both of these. I'm going to find the change in potential first. Why? Because I have this R stored on my calculator, and I think that's where I'm going to use it. So what's the change in potential? What's change in anything? This is going to be negative big G, big M, little m over our final minus negative big G, big M, little m over our initial. It's going to be negative 6.67 times 10 to the negative 11. 5.98 times 10 to the 24th. What was little m? I've scrolled down. 1800? What's our final? Oh yeah, our orb. So I'm going to write 2.26 times 10 to the 7th. But what button am I going to hit there? My answer button, definitely. What's a minus minus the same as? Plus. And then for those of you who were away and haven't watched the video lesson, here's what we said, Camille. Is the top here and here, here and here, here and here, are the top three things identical in both fractions? I'm going to put a little ditto mark times ditto mark. That means put the same thing in there. And I'm actually going to do that on my calculator as well. But what's our initial? Radius of the Earth. Okay. And we're going to enter the first term into our calculator, hit equals, write it down to about 5 sig figs, enter the second term, hit equals, write it down to about 5 sig figs, and then crunch it. So we're going to go like this, negative 6.67 times, no, not times, Mr. Dewick, scientific notation button, negative 11, times 5.98, scientific notation button, 24, times 1800, divided by answer button. And I get, wow, worked out nice, negative 3.1752 times 10 to the 10th. One 752 times 10 to the 10th plus. And then, Naomi, what we said is we're going to backspace and edit because all of the numbers are identical. We're just going to delete the negative because the second term is positive, and we're just going to change the denominator and put the new one that we want and hit equals. And I get 1.1253 times 10 to the 11th. 1.1253. 1.1253 times 10 to the 11th. And I hope you're all at the stage where you can get those now. And now we're going to combine these. So it's going to be negative 3.1752 scientific notation button 10 plus, hey, I can just hit answer button. And I find that the change in potential energy is 8.0781 times 10 to the 10th. 8.0781. 8.0781. Now, if you're not getting that, later on in today's lesson, snag me and we'll walk through it. I usually put a box around this because I know I'm going to use it later and I don't want to lose it. But we're not done. What else do we have to find? Change in kinetic. Okay. What's change in anything? This is going to be a half mv final squared minus a half mv initial squared. Where did we decide that we were always going to launch from? Superman's Fortress of Solitude or Santa's Workshop from the North Pole, and that allowed us to say that our initial kinetic energy was 0. If we launched further along the Earth, we'd have the Earth's rotation to take into account, so we're doing a lovely cheat. Do I know V final? They gave it to me? What if they hadn't? Gravity is what's pulling me in a circle, and I'd solve for V. Because we're in orbit. This is going to be 0.5 times 1800 times, was V 4200? Squared. 0.5 times 1800 times 4200 squared. And I get 1.5876 times 10 to the 10th. We're not done. What did this question want me to find? Work. So what will I do with these two numbers in the box? Okay. Work is going to be 8.0781 times 10 to the 10th plus 1.5876 times 10 to the 10th. 8.0781 times 10 to the 10th plus answer button, and I get 9.67 if I go to 3 sig figs now times 10 to the 10th. Because we're doing so much crunching and using answers to find more answers, I'll be fussy to 2 sig figs. If your third sig fig is off by 1, I'm not going to freak out. So if you had said 9.66 because you would round it off a little differently from me along the way, I'm good with that. Is that a lot of energy? It's why it's expensive to put stuff into orbit. What's your homework? So I had already said try 1, 2, 3, and 7. You can try number 9. Let me just see here. I want to give you practice with this, so I'm going to skip 10. 11 is good from the notes. 14 is good. 15 is good. Got a lot of people away. I was going to start the next lesson, but I think we'll press pause here, or will I also give you your take-home quiz? I think we'll press pause here.